All right, for this live code walkthrough, let's talk about the Drake equation. So the Drake equation was created by Frank Drake, and really what it was is a way for us to open up the avenue for asking questions about, is there life out there? So this equation is basically built off of a number of different factors that people believe would have to be considered when we're considering if there is life out there. So N would be the number of civilizations that would be able to contact us in the Milky Way galaxy. Okay. R star, this is the rate of formation of stars suitable for the development of life. So there are some kind of values that we are looking at on R star. There is, Wikipedia, as much as you want to rely on it, there are some values. So here's original estimates, and we have other ones. So here, this would be new, gives a star formation rate of about 1.5 to 3 stars per year. This is for the Milky Way galaxy. Now, what do they mean suitable for development of intelligent life? Now, if we look at the HR diagram, this is an HR diagram, Hertzsprung-Russell diagram, and this is supposed to be the life cycle of a star. We are in the main sequence. We're right around here at 1 for our sun. That's the luminosity of a sun, the brightness of our sun, and we're right around here. Okay, and there are some stars that we are not going to be able to sustain life. White dwarfs, which could lead into black holes, supergiants, those type of things. We would not see them. But on the main sequence, we do believe that we should be able to see life somewhere maybe around here to here. Okay. So we would want to be able to consider that as a factor. And then any of the f of ones, these are fractions. So they can have values that go from 0 to 1. 1 would be 100%, 0 would be 0%. So f of p, that would be the fraction of those stars with planetary systems. What is the original estimates? They say 0.2 to 0.5. And here, analysis of microlensing in 2012, that they found that f of p may approach 1. That is, all stars have some planets, as a rule, are going around it. And then instead of having planets rotating around the star is not the exception, it's the rule, it's the default. Okay, so we would build with that. N of E, that is the number of planets per solar system, so the number of planets that are rotating around one of those stars with an environment suitable for life. So what is that? Well, the Goldilocks zone, that's what that's considered. Now, what is Goldilocks zone? What does that mean? Well, if you guys are familiar with Goldilocks and the Three Bears, Goldilocks, basically did a B&E, went into someone's house, the bear's home, and tried their porridge. One was too hot, one was too cold, one was just right. Slept in the beds, one was too hard, one was too soft, one was just right. Okay, so Goldilocks zone stands for the conditions are just right. Now, what type of conditions? Well, most people believe that in order for life to be sustained, we would need to have at least at some point in its cycle, at least have water that can be liquid. If we're too cold, then it stays frozen and we can't sustain life. If it's too hot, it could boil away in the atmosphere and we would lose our atmosphere. So if we're looking at Mars and the other planets that are right around us, this falls outside of the Goldilocks zone. So we're saying Earth does have liquid water, so it should be able to sustain life, and it does. Okay, now going back to Wikipedia, let's see what we have. They're saying, since there are 100 billion stars in the galaxy, this implies that f of p times n of e is roughly 0.4. Now, since we are saying f of p, pretty much every planet is closer to 1, every star has planets. So N of E would be closer to about 0.4, the nearest planet in the habitable zone. So we're saying that of the stars that are going around, we are close to half of them should have at least one planet that has that's able to sustain life with liquid water. Okay, so we just keep going down this. F of L is a fraction of suitable planets where life actually does occur. And, I mean, it's never going to be 0 because we are life that does occur. So we could pick values that are, within that range. It should not be 0, but since we don't see that everywhere, and some of that is just because we have not been able to make it there, what all can be formed as natural part of evolution framework. F of L and F of I and F of C are all set to a probability of 1. This result calculation concludes that there are more than 30 current technological civilizations in the galaxy. So this is what they're estimating. Now you guys could pick different values for that. Now, so what we would assume is that, okay, of all the life that has developed on these, what is the percentage? So that's between 0 and 1, and again, we can't do exact 0 of those that have developed intelligent life. So we're not just talking about, plants or insects. We're talking about intelligent life that's capable of thought. Okay, and then of those which have developed the technology to produce detectable signs of existence. So they've been able to communicate outside of their atmosphere. And then finally, the average length of time such civilizations produce such signs. If we went and looked just at us as a baseline, first radio signal, we're looking at 1897. Sent the world's first radio message across open water. Okay, so if we did that, 1897, we're looking at 2023 minus 1897. That is 126 years. Now let's see what they got down here. Okay, this individual, I don't know who this is, American science writer, he says 420 years, 304 years. And, it could be much larger. Let's say that we have, we're estimating that there are civilizations that have been able to communicate and they live 10,000 years. Maybe we are just a young species in this. Okay, so that's what we're going to build. We're going to quickly build this using P5JS. Okay, now because of this, we want to be able to kind of create a function that we could use multiple times. Right now, I'm just going to kind of hand jam this in for these values. So we want to split this up. Let's do 2 separate. We're going to build this. Okay. Each one of these we're going to pass in, and we can start putting some values. So we're going to do let R star F of P, N of E, F of L, F of I, F of C, and L. Okay, those are what we're going to compute. We're going to give values for each one of those. So R star, we already seen had a value of, let's move this over here. R star had a value of, current is 1.5 to 3. So let's say 2. Let's do F of P, fraction of those that have planets, and they said that it was approaching 1. So let's do 0.9. Then we do our N of E, which we seen was closer to 4. So 0.4. We have F of L. Now they were saying of these that are capable of developing life will develop life. Do we believe that 100%? Maybe not. So let's do, instead of a 100%, I'm going to say, I don't know, 0.7. For intelligent life, I'm going to say half of those, 0.5. For those that are able to communicate, I'm going to say it's much lower. So let's say 0.2%, only 20% of those. And then for my L, I want to say, let's say 10,000 years. Okay, so that is my equation. Now, when we look at how this is built, everything is multiplying. So we are returning n. So on here, we say let n is equal to r star times f of p times n of e times f of l times f of I times f of c times l. To make sure I type them right. And then we could print out on our console. Let's just do console.log, and we'll use a string literal. The number of civilizations. Actually, we'll just return it here. Return. Now I'm using the backtick. It's the key that's above the tab key to the left of the 1 key. Intelligent species in the Milky Way galaxy is $ code block n. So why haven't we heard from them? Okay, so I've built my equation. Now, if I click the play button down here, we have a little caret. I can type up the equation, the function that I just built, equation, and run it by hitting enter. By those calculations that we gave right here, this is 504. That's kind of amazing. Now, let's make this so that this is a little bit more reusable. Instead of having it where we are putting these values, we want to put these where they, when we call this equation, we are writing them. So R star, FP, and E, FL, FI, FC, and L. Okay, which would mean that we don't need these at all. We're passing these in when we call it. So when we run, now I can click up on my keyboard to be able to just call the last equation that I did, and I can, just so we see that it's working the exact same, give these values. Okay, I'm separating each one with commas. 0.7, 0.5, 0.2, and 10,000. Okay, now I click enter. It works the exact same, but now I could say, you know what? What if that was at 3? We formed 3 stars in the Milky Way galaxy. That was the only thing. That went up to 756. What if I wanted to modify this more? And I wanted to say, well, f of p was 0.9. Let's do f of L, we are saying as 7, and they said that that should have been a definite. They said it should be 1, 1, that we would end up developing life. We're at 2160. What if the length of that civilization's life was closer to 1,000 years? That still is pretty high. Okay, so on all of these, we were over 1. I mean, just to try to get it to 1, let's try to bump it down. 1.5, f of p, let's say that that's not high. Let's say that's 0.2. I don't know, 0.2, 0.2. That's closer to 1. Let's see if we can get it to, we have 126 years. Bumps us a little bit down. It can never really be below 1. That would be one of the things that does not make sense because we are a species. But we could play with these numbers. So really what this ends up pointing out is that why have we not heard from these people? And that's what SETI is, the Search for Extraterrestrial Intelligence. Basically, they have a big bank of satellites, and they use those to try to test if there's life out there, to try to receive signals and see what's if anybody is answering back. We have sent out the Voyager satellites to try to communicate to other life out there. So if we haven't heard from them, I mean, there could be a number of things that we would need to consider. Maybe we are too minuscule for the other civilizations to really bother to talk to us. So in this case, we would be the ant, and they would be the boot. Maybe it's not that way. Maybe it's the other way around. Maybe we are the boot and they are the ant. So even though they're capable of communicating, they're afraid to communicate because we are a warring country, nation, and world. We tend to start wars. Maybe it's something different. Maybe we can't understand how they are communicating, or they can't understand how we are communicating. Maybe it's because they are on the complete opposite side of the Milky Way galaxy, so their communication has not even reached us yet. Or maybe there was some type of bottleneck that has happened in the past. A bottleneck might be, some cataclysmic event that has dwindled the civilizations and species and life-bearing planets down to almost nothing. Maybe something like the black hole or the Big Bang. Maybe that's what occurred and all life was destroyed, and we are the first to come out of the primordial ooze. So just interesting things for us to consider using the Drake equation, being able to do this in code. All right, good luck. Have fun.